Hello there! Did you really believe that attention is all you need? According to the papers of the last weeks, not anymore. In today's video, we showcase the FNet paper replacing the self-attention in BERT with Fourier transforms. Fourier what? Miss Coffee Bean, did you know it all along that self-attention is doomed? Then why didn't you tell me? Is it because I left you in the coffee roaster for such a long time? Here we go. The FNet proposed in this paper does one modification to the transformer architecture, but this one thing has quite the impact. For a bit of a context here, the transformer, composed of self-attention, followed by fully connected layers, and not to forget about the residual connections and layer normalization, had been proven to be extremely successful on multiple data modalities. It started with text, became mainstream on both image and text, then on image only. Watch Miss Coffee Bean's videos for all of this. Then it moved on to speech and even further than that. But powerful as it is, the transformer has a problem. The self-attention mechanism scales quadratically in time and memory with increasing sequence length. In other words, there is a limit to what the length of your text might be. For images, the size or resolution also determines the sequence length, and with usual transformers you can reach the sequence length limit quite fast. So far, methods to reduce this quadratically scaling attention to a linearly scaling operation have left the concept of attention untouched. Methods like linformer, performer, and others have cleverly approximated self-attention matrices, sped up computations, and enabled much longer sequences, but the concept of attention stayed mostly as it was. Well, so far. Because now heretic papers are coming out and rebel against attention. No, it's not attention that we need anymore. Miss Coffee Bean, is machine learning now a teenager and doesn't want attention anymore? Because this is exactly what FNet also does. It replaces the self-attention layers through Fourier transforms. But the most important question here is, how dare the authors make such a move and not call their paper Fourier is all you need? The audacity of these authors is unbelievable. Sarcasm. Okay, so let's see how this replacement of attention works and what it brings. The FNet authors take the classical transformer block and modify it by replacing the self-attention layer containing learnable parameters with an unparameterized, thus not a learned transformation, being the Fourier transform. So before, for each token, self-attention layers were learning to compute importance scores for the token given all other tokens. So to emphasize, the computation of the importance is learned from data, is task specific. And the new representation for each token was the sum of all tokens weighted by their importance to the original token. Now, with the Fourier transform, the new representation for a token is not learned, but it is a predefined mixing scheme of tokens. This makes this whole thing faster because this layer doesn't perform any gradient updates, but is also unchanged from task to task or one training scenario to another. The mixing scheme of the tokens is following the rules of the Fourier transformation. Now, what exactly is this? This is where the math gets a little complicated, but it does not need to scare you. Here it is just written that each token is multiplied by sines and cosines, because this e to the power of something we can write as a superposition of sines and cosines, hand wavy, like this. So, for example, the first token is a weighted sum of all other tokens, but here the weights are modulated by sines and cosines. But because we are at the first token, where k equals 0, the frequency of the sines of cosines hidden in this exponential is 0. So the first token is just the sum of all other tokens. For the second token, the modulation is more interesting by superimposing waves that increase in frequency as we add more tokens. For the third token, the frequency of each wave we add increases even more, like this. To put it as an analogy, the new representation of each token is like a cake. where the base frequency is still the first token, then the second token adds some detail and becomes the cream on the cake, then the third token becomes the even more detailed icing, the fourth token is the super detailed nuts, and so on, and then the whole cake is the new token representation, because we take the summation of all of this. And to be fair, all of this has real and complex components, but forget about it, because after all the operations are computed, the authors delete the imaginary component. Anyway, the important messages here are: firstly, the Fourier transform applied to tokens mixes the tokens among themselves. It's kind of similar to what self-attention does, but self-attention learned the weights by which these things need to be mixed. Also, the same thing is done to the hidden dimensions, so that the features of the tokens are also mixed among each other. And until here, the transformation that was done is reversible by the inverse Fourier transform. In other words, the components of the cake can be recovered by decomposing after each frequency. It is the next step, the feed-forward layers, that mix things even more, and usually not in an invertible way. The second important message is that the mixing scheme or pattern is not learned. It is fixed and always follows the same rule, making the architecture simpler and easier to compute. It decreases the number of the learnable parameters of the transformer, which now is technically FNet and not the transformer. Thirdly, a more advanced take-home message also mentioned in the paper, which Miss Coffee Bean found super interesting, is the following. You maybe know, or if not, just take Miss Coffee Bean's word for it. Convolutions in the real/time domain corresponds to simple multiplications in the Fourier/frequency domain. So the first Fourier layer of the architecture moves the representation from the real domain to the Fourier domain, and multiplications in these layers happening afterwards are now actually convolutions in the real space. So by adding more and more transformer layers, each one with one Fourier layer, FNet is jumping back and forth from multiplications to convolutions. In other words, convolutions are somehow here and perhaps now are taking revenge on the transformer and crash their party. Are convolutions all you need? I actually cannot hear all you need anymore, but Miss Coffee Bean makes me say it. Okay, but one question remains. Why exactly the Fourier transform? Reading the paper, it becomes clear that the first thing the authors tried was simple linear mixing schemes, but then went with something more structured like the Fourier transform. But believe it or not, the other paper getting rid of attention, the MLP-Mixer, learns mixing patterns that look very much like Fourier. Just look, here is the base frequency, here is the double of that frequency with its negative counterpart. The MLP-Mixer found something like a Fourier scheme on itself, but on images. FNet has been applied to text and has the Fourier transformation hard-coded, and it seems to work also well. So the FNet basically is a BERT variant without attention, but Fourier transformations, and achieves 92% of the accuracy of BERT on glue, an important NLU benchmark, which is not exactly 100% of BERT, but good enough, and especially because there is no quadratically scaling attention anymore, it runs 7 times faster on GPU and 2 times faster on TPUs, and you can increase the sequence length. So self-attention was praised as being the recipe to success for quite a while. But now papers like FNet, MLP-Mixer and GMLP relativize this by a bit, showing that if there is enough data and compute, the architecture does not matter much. So it seems like back in the days when MLPs were a thing, we discarded MLPs too early, when perhaps the only thing that was missing then was the data and compute scale we have now. So we preferred CNNs or RNNs because of their inductive biases. Always a good idea with little data. But to say this is very unfair because architectures like FNet or MLP-Mixer are not exactly like a vanilla MLP from back then. The structure of these MLPs follows the trend set by transformers. So Miss Coffee Bean sees this as an evolution and not really as a backwards involution or something. In any case, now that we have seen that long sequences are not such of a problem anymore and that image token mixing and text token mixing looks quite similar, Miss Coffee Bean thinks it's great news for multimodality, where the goal is to combine many types of input data that potentially comes in very long sequences, especially if you append one modality to another, like vision and language transformers do. The FNet paper is very well written, so what are you waiting for? Leave a like, subscribe, share Miss Coffee Bean to send her around the world, and go read the paper yourself. Okay, bye. Miss Coffee Bean, it has been a while since your last video. Are you getting lazy or what? Oh, yes, I know I put you in the coffee roaster and left you there, but I was busy with moving and with a paper. No, I did not waste my time. No, Miss Coffee Bean, that's rude to say. Go to your coffee roaster.